Hi everyone, welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our distinguished speaker, Professor Susan Murphy from Harvard University. Professor Murphy will be delivering this talk with her postdoc, Peng Liao. Professor Murphy is Professor of Statistics and Computer Science and a Radcliffe Alumni Professor at the Radcliffe Institute at Harvard University. She has made fundamental contributions in mathematical statistics and personalized medicines. Her current research focuses on improving sequential individualized decision-making in health, in particular on clinical trial design and data analysis to inform the development of just-in-time adaptive interventions in mobile health. Professor Murphy is the former editor of the Annals of Statistics. She was awarded a MacArthur Fellowship in 2013, elected a member of the National Academy of Medicine in 2016, and she was also elected as a member of the National Academy of Science. In the year 2018, she was the R.A. Fisher Lecturer and was elected president of the Institute of Mathematical Statistics. Peng Liao is currently a postdoc research fellow in the Department of Statistics at Harvard University, advised by Professor Murphy. Prior to joining Harvard, he received a doctorate degree in statistics from the University of Michigan and a bachelor's degree in statistics from Sun Yat-sen University. His research interest lies in sequential decision-making problems with applications in mobile health. The title today of their talk is Off-Policy Estimation of Long-Term Average Outcomes with Applications to Mobile Health. Please join me in welcoming them.
Thanks. So I'm going to give the intro. Peng is going to make the slides move for me, and then he'll take over. So this work is motivated by mobile health, but there's a number of areas in which this type of work is also relevant. Many of you know about online education. This is a setting in which this very similar problem occurs. Also in businesses, long-term retention of customers, how you communicate repeatedly over time in order to retain them for longer periods. And in the clinical setting, particularly in a hospital type setting, clinicians get sequences of alerts. And there's enormous interest in understanding when you should alert clinicians and which alerts will actually result in any kind of impact on the clinician's behavior. Okay, Peng, you want to go to the next slide? So I'm going to give the intro and explain why we're interested in this particular framing of the problem, and then Peng will take over. Okay, Peng. Next slide. Okay, so one of the issues, well, in digital or mobile health is it's an exciting area for people like us because you can collect real-time data from a variety of wearables, sensors. We now have wearables that are sewn into individuals' clothing. So you can not only collect data in real time as people go about their lives, you can also push treatments or interventions to people any place, anytime. So these are called, you see in that second bullet point, it says push intervention. So this is like a treatment. It might be a reminder about medications. It might be some suggestion about how to, what kind of food to shop for because you're near a particular grocery store. These interventions are intended to help the individual make decisions at that moment. And so, as you can imagine, these are all sequential decision-making problems, and the goal is always to form some sort of policy which will result in high-quality outcomes, increased utility over a period of time. In the mobile health community, these policies are called just-in-time adaptive interventions. That's just the word that's used in that world. And the big reason why from a data science perspective, we're really interested in this, is that these interventions, if you're not careful about when you send them, sending them in the right time, or not sending them too much, they can have effects which move the individual to a state in which they're much less receptive to any kind of treatment. So in that type of setting in which if an individual gets moved, if there is a potential that an intervention or a treatment or a message will move the individual to a state where they're less receptive, less able to make use of the treatment, this is exactly the setting where you really want to pay attention to sequential decision making. Of course, one also wants to help people have form good habits and so on. So you also want them to move to improved states. Avoid moving to bad states, states where they're overly burdened, and improve movement to good states. Again, so this is this balancing between short-term and long-term. That's essentially what I just said. And the longer goal is to maintain good behaviors over a longer period of time. Pung, can you go to the next slide? Yeah, so the reason why we're interested in a longer period of time is many of these interventions are intended for individuals who have chronic disorders, or even if they're not chronic, the period of time is long. For example, in a take-home chemotherapy, you might they may need to be really adherent for a period of 3 years. And that's a long time. They have to be adherent every single day, day in and day out for 3 years. Or if they have a chronic disorder like hypertension, this is for the rest of their life. People need to try to manage that illness. Now, if you go to the actual policies that are being promulgated by health maintenance organizations and so on, for the most part, they're expert systems. That means that maybe some data analyses were run, some experts got together, and they made up decision rules, they formed decision rules that they would then use and actually implement. And so one of the reasons why we're interested in this work is we want to think about a longer term use. And how do you use data to inform whether or not an expert system really has very good performance over a longer use? And for the most, when people test these expert systems, they're normally tested for short periods of time. So what's the problem? These are batch problems because you have a data set in which the actual data was collected under some policy, not necessarily the expert system or the policy you're interested in. That's why it's called off policy. And it's a batch of data, so the data set is sitting in front of you. It's not the online setting. And you want to go and now anticipate what would be the impact if you were to use this policy in future for this type of population. I think, Pung, you must be on from now on, right?
One more slide.
Oh, one more slide. Okay, yeah. If you've heard me speak before, you know this is, we're involved in a large number of these types of studies, but this particular study is really, it's about physical activity for individuals. The goal, it's a whole series of studies, but it is for individuals with stage 1 hypertension. The idea is if you can help them change their lives, they may not have to go on to medications. And in this particular one, at each of 5 times a day, these are individual specific times, an individual might be given a message about a kind of activity they could do wherever they are. The content of these messages is tailored to the sensor data on the individual at that time. But we focus on whether or not to send the message or not. And the reason we do that is because it's so aggravating to get these suggestions, particularly if they're sent in the wrong at a bad time for you. So the first study of this series of studies was only for 6 weeks. And these suggestions were randomized at each of 5 times a day with probability 0.6, so around 3 messages. A person would get around 3 messages a day. And that's going to be the data that Pung will show us later on that he'll use to evaluate a policy. Okay.
So I'm going to continue the talk. So I'm going to first talk about the distributional assumption that we impose on the collected data and formally define our goal and how we assess the longer term performance of a given treatment policies. So on each individual, we observe a trajectory, longitudinal data, and we use the little t to index the decision times, and s to denote the individual state, and a to denote the actions or the treatments, assignment at its decision time, and we use r to denote the proximal outcome, or we call it the reward. The proximal outcome is usually defined to measure the near-term impact of the current actions, and that is why we also call it the proximal outcomes. And in the case of HeartSteps, the T, we have 5 decision times per day, and the ST includes all kinds of information that we've collected on the participants using the sensors. For example, we have the location, we have the weather, and the activity level, and all kinds of summaries of the prior activity as well. And throughout this talk, I will assume the state space is discrete and finite, and this is just to simplify the presentation, and the results can be generalized to more general state space with more technical conditions. And in the case of HeartSteps, the action is binary, and the reward in the HeartSteps is the 30-minute step count following each decision time. Right. So we're gonna assume that the evolution of the states satisfy the Markov property, meaning that given the current state and action, the next state is conditionally independent of all of the previous state and actions. And furthermore, we're going to assume that the transition probability does not depend on time, so it's just time stationary, and we use P to denote the transition probability. So to ensure the Markov property, essentially we require the state to be a high quality summary of the past observation and actions. And the stationarity is also a big assumption. In mobile health, we are likely to see non-stationarity in the form of engagement or burn. So it's critical we collect enough information on each individual so that we can hope for the the stationarity of the transitions. And in the literature, this formulation is also called the Markov decision process. And we assume that the treatments in the collected data are randomized according to a behavior policy with known and strictly positive probabilities, as in the case of the micro-randomized trials. So we're not talking about the observational study for this work. So what is our goal? So suppose we're given a pre-specified Markovian policies that we consider for use in the future. This could be expert constructed policies, and we are interested in assessing its long-term performance. And we use pi a given s to denote the probability of choosing the action A in the state S. So what is our goal? So given a data set that consists of NID copies of the trajectory, our goal is to conduct inference for the long-term average reward for the target policies. We denote it by eta pi. It's a function of state in general. It's a limit of the expected rewards given the initial state S, and we let the t goes to infinity. T star goes to infinity. Here the expectation, we have this subscript pi. This is to so the expectation is taken with respect to the distribution of the trajectory, in which the state transition is still p as in generating the data, but now the actions are selected by the policy pi instead of the behavioral policies. Right, because we're assuming the state space is finite, so this limit here is well defined. But in general, the limit may not exist, and one can define the average reward using some sort of upper limit instead of yes. So things will be more complicated for the general state space. So each policy actually induces a Markov chain on the state with the transition probability p pi. So basically, we're just averaging out how we select the actions. And when the induced Markov chain is irreducible, so we're gonna assume that the induced Markov chain is irreducible. The irreducible meaning that for every two states in the state, they can communicate with each other. Obviously, this assumption implies that any time invariant information cannot be included in the state because they not change over time. So there's no way you can communicate with each other. But in the paper, we do extend the methods to incorporate the baseline information. But for today, I will just focus on the case where the irreducibility assumption holds. Right. So under these assumptions, the average reward is now, we can show that the average reward is independent of the initial state. So it's a constant, and this constant can be calculated as the average, as the expected rewards under the stationary distribution. So here R sub SA is the expected rewards, and the d pi is the stationary distribution for the induced Markov chain. And the existence of the stationary distribution is also guaranteed by the irreducibility assumptions on the p pi. Right. So why we are interested in the average reward? Remember that the goal is to assess the longer-term performance of a mobile health policies, and the average reward provides a high-quality proxy for the expected rewards over a long period of time. In fact, we can show that the bias of the final average reward decreases as the order of 1 over t star instead of the 1 over square root t. So that's why it's a high-quality proxy. Of course, the leading constant will depend on the mixing time of the induced Markov chain. Right. The reason why we are able to kind of estimate or assess the eta pi is because even though we only have on each individual we only have the first t time points, it's because we assume the Markov and time stationarity assumption, which will allows us to estimate this quantity that is essentially defined over infinite time horizons, even though we only have t time points data. Right. So back to the HeartSteps example. Remember, in HeartSteps, the reward is the 30-minute step count following each decision time. So our goal is to use the data from this 42-day micro-randomized trial study to estimate eta pi. Eta pi is a proxy for the average of the 30-minute step count over a long period of time. For example, like a year, when we use the pi to select to determine whether or not to send the activity suggestions. And the behavioral policies, that is the policy under which the data is collected, is not necessarily the target policy that we want to assess. In HeartSteps, the behavioral policy is simply to randomize with a fixed probability 0.6, but the target policy can be much more useful. So now I'm going to talk about how we construct the estimator for the average reward. So first, I will need to introduce the relative value function. It's a state action function. For each little t, we are calculating we are looking at the expected cumulative difference between the reward under policy pi and the average reward, the long-term average reward, given the initial state and the initial actions. And this is a Sathera sequence, and that is the limit of the Sathera mean sequences. If the limit is well defined in the case of finite state, and when the induced Markov chain is actually aperiodic, the expression for this relative value function can be simplified to just the ordinary limit by taking the t goes to infinity. Right. So the relative value function and the average reward are closely related through the so-called Bellman equations. So on the left-hand side, we have the conditional expectation of the reward plus the average value of the next state. And the Bellman equation says that the true average reward plus the relative value function at the current state action is going to be same as the expected reward plus the expected next state. It can be shown that the solution is unique for the eta pi for the average reward, but up to a constant for the value function. So our estimator for the average reward is based on solving the Bellman equations in some sense. It is sufficient to learn a specific version of the value function. For example, we can target the value function such that the value at a particular state, S star and A star, is equal to 0. Right. So we will introduce the notion of the so-called Bellman arrow. So the Bellman arrow, we're just taking the Bellman it's just the Bellman equations. So solving the Bellman equations now is equivalent to finding the eta and q such that the Bellman arrow is 0 for all the state action pairs. Right. So how one might construct the estimator for the average reward and the value function, because we know the Bellman arrow should be 0 at the true average reward and the value function. So a natural idea is just to replace the conditional expectation by the realization and then minimize the square of this plugging arrow to obtain the estimator for the average reward and the value function. Unfortunately, unlike in the classical regression problem, the dependent variable here involve this unknown q. As a result, it's straightforward to show that the true average reward and the value function does not really minimize the limit version of this objective function. So this is a bias estimator. Right. So there are a couple ways you can get around this bias issue. One easiest way would be to develop the z estimator or the estimating equations. Unfortunately, the z estimator might suffer the computational problem, especially when the function space is complex or when we have limited data. So in this work, we use the idea of the coupled estimator, which is essentially solving a series of M estimator problems. So I will first talk about the high-level idea of what this coupled estimator is. So for each eta and q, we will project the Bellman arrow into a function space G, and we denote the projection by this G hat. So it's a state action function, and it depends on the eta and q. So for each given eta and q, we have this Bellman arrow, and then to obtain the estimator of the average reward and the value function, we minimize the square of the projected Bellman arrow over all possible eta, and q belongs to a function space that we call it q. Right. So that's the idea of the coupled estimator. So informing the to form the projected Bellman arrow, we use the space G instead of the space Q, because remember that the Bellman equations only identifies the value up to a constant. So we just need to target one specific value function, right, such that like the value is equal to 0 at a particular state and actions. So we constrain the function space Q such that it is at some particular state action, the value is always equal to 0. But this constraint needs not to be placed on the members of G, which we use to construct the Bellman arrow. So a natural choice for G is by relaxing that constraint by adding a arbitrary constant to the members in the function space Q. So so how we so when the state space is high dimensional or complex, we might want to use a flexible function space to do the approximation. So in this case, we will, instead of using a standard M estimator, we might want to use a penalized estimator. And here we use the J2 is a regularization term that measures the complexity of the functions in G, and mu n is tuning parameters, and this is classic estimator in the non-parametric regression problem. And similar to the construction of the projective Bellman arrow, we can estimate the eta pi and q pi by solving a penalized regularized objective functions, and J1 is another regularization term that measures the complexity of Q, and lambda n is a tuning parameter. So in the optimization, this is called the nested or coupled estimation, because in this objective function we have the G hat is a solution of another optimization problem. That's why it is called nested. Fortunately, when both Q and G are reproducing kernel Hilbert space, we can find the closed form solutions for the eta hat. Yes. So so now I'm going to present some theoretical results for the proposed estimator. So first, I will introduce some notations for a state action functions. We use the norm without any subscript to denote like the average norm over t time points. Here, the expectation is with respect to the trajectory under in which the actions are selected by the behavior policies, and we will denote the Bellman arrow using this notation E pi. Again, it's a function of state and action, and it depends on eta and q. We use the G pi star to denote the projected the population level, the population version of the projected Bellman arrow. So our first assumption is that a shifted version of the value function belongs to the space Q. And our second assumption is on the complexity of the space G. If we're restricting the eta and q such that the norm of the Bellman arrow is equal to 1, we assume that the infimum of the norm of the projected Bellman arrow has to be positive. In the case of in the case where the both function space is linear, this assumption is akin to assuming some sort of smallest eigenvalue is greater than 0. And notice that here we're not assuming that every Bellman arrow belongs to the space of G. Instead, we only need to ensure that the space of G is rich enough so that this infimum is strictly positive. Yes, because in the case where every Bellman arrow belongs to G, this infimum will be just 1. Here we just need to ensure this is the infimum is a positive number. So our next assumption is the classic entropy conditions on the two function classes. Here, this curly n is just the covering number with respect to the Shoup norm, and alpha is a constant between 0 and 1. Here, for simplicity, we take the max of these two function classes. One is on G, one is on Q, instead of having two separate alpha. Alpha is just measures the larger value of the alpha, the more complex of the function space is. Right. And so So together with some other regularity conditions, we are able to bound the norm of the Bellman error at the estimated average reward and value functions. Here I present a simplified version where the tuning parameters are selected in the optimal rate. And please refer to the paper if you're interested in the more general case. So just to remind you, this norm without the subscript is the average L2 norm over t decision times, and this epsilon pi, e pi, is the Bellman error. So when the tuning parameters are selected optimally, the square of this Bellman error converges to 0 in the order of 1 over n to the power of 1 over 1 plus alpha. Remember, alpha is the number in the matrix entropy. So this is the optimal rate that you can get in a similar regression problem where the function space satisfy those matrix entropy conditions, and you can show that the bias of the estimated average reward is actually bounded up to a constant by the norm of the Bellman error. So this result shows that the estimated average reward is a consistent estimator. Here I skip some other regularity conditions. This includes some boundedness assumptions and irregularity assumptions on the regularization term. Please refer to the paper if you're interested in the details. So now we'll move on to the asymptotic normality for the estimated average reward. So we will introduce two additional notations, and the d pi SA is the density of the stationary distribution of the state action pair under the target policies. So it can be written as d pi s times the pi a given s. And pi a given s is the probability of selecting action A at the state s. And we use this d bar t of SA to denote the average density of the distribution of the state action pair, averaging over t decision time points in the data collected under the behavioral policies. So it's so each little t, the dTSA is the marginal density for the state action at the t time points, and we're taking the average over t time points to get this d bar t. So now we are ready to present the asymptotic normality of the estimated average reward. So under the assumption of the previous theorem and some additional regularity conditions, we can show that the estimated average reward is asymptotically normal. We can see that the average, the asymptotic variance involves this density ratio of the two this density ratio. And remember that the numerator is the stationary distribution, and the denominator is the average density under the behavioral policies. As one will imagine, one of the critical assumption is that this density ratio is well defined. So not only we require the support of the action under the behavioral policies covers the target policies, we also need to ensure that the support of the state distribution under the behavioral policy also covers the stationary distribution under the target policies. So this is different to the classical one-time point problem where the importance weights only involve the actions. But here, in this infinite horizon setting, we also need to correct the distribution of the states. So to construct the inference, we need to estimate this asymptotic variance, which requires us to estimate the density ratio. So instead of directly estimating two densities and then just divide the two density estimator, in the paper we relate this density ratio to a new value function with a new reward, and then we develop a coupled estimator for that new value function, and then we convert that estimated value function into the estimator of the density ratio. But for because of time, I don't I'm not going to talk about that in detail, but feel free to look at the paper if you want to know the details of that, how we construct that new couple estimator. Okay, so we can from the expression of the asymptotic variance, we see that there are actually three factors that impact the estimation error. One is the closeness between the two density ratio, and also the variance of the so-called temporal difference error, temporal difference distance, and also the length of t, as the variance is taking over the average over t time points, right? So if we want to, if we make a simplifying assumption that the conditional variance of this TD error is a constant, does not depend on state and action, then the asymptotic variance can be simplified to this formulation, to this formula, and we can clearly see that as t increase, we have smaller asymptotic variance as when we expect. And if the distribution of state action is closer to the stationary distribution, we will also have a smaller asymptotic variance. Right. Okay, so far we've focused on estimating the average reward of a single policy. All of the results can be extended to evaluate multiple policies. In particular, we can show that the joint distribution of the estimated average reward converges to a multivariate normal distribution, and these results can be used to compare two policies of interest. Okay, so I will talk about some numerical examples. So first we conduct a simulation study to demonstrate the validity of our proposed method in the finite sample setting. And for this simulation, we have a two-dimensional state, and the action is binary, and we have two policies that we evaluate and compare, the always true policy and no Truman policies. And in the implementation, for both function space Q and G, we use the reproducing kernel Hilbert space with the standard RBF kernel, and the tuning parameter are actually selected. We have two tuning parameters, lambda n and mu n. And these tuning parameters are selected by cross-validation procedure, which is different to the classical cross-validation in the supervised learning problem. Please see the paper for the details. And this table shows the simulation results of the policy evaluation, the case 1 and case 2, and also the comparing two policies, which is case 3. As we can see in small samples, especially when t is also small, the coverage probability of the 95% confidence interval is slightly smaller than the desired 95%. But when t is large, but when n gets larger, when n and t gets larger, the coverage probability get close to the nominal level, which is surprising because here we only have 40 trajectories, but the asymptotic is already able to give us the good approximations. And this, so now we talk about the application to the HeartSteps. Just to remember, HeartSteps is a 42-day study with 37 participants, and decision times is 5 times per day. So we have in total 210 decision times, and the action is whether or not to send the activity message, and the states includes the step count, summary, location, temperature, and also the number of the past notifications. The reward is the 30-minute step count after each decision times. So we consider two policies. The first policy is to send the activity message when the participant is at either home or work location, and the second policy is like the opposite of the first one, is to send the activity message when the participant is not at home or work location. And this comparison is of interest because people at home or work are in more structured environment, and thus might be able to better respond to a activity suggestion message as opposed to at the other locations. In fact, our data analysis did indicate that the effect of the message on the immediate reward is actually lower when the participant is at the other locations. Unfortunately, this does not really translate to the long-term average reward. As we can see, the estimated average reward for the first policy is slightly better than the other one. However, the confidence is not really significant. The confidence interval does include the 0. We suspect this may be due to the small samples, as we only have 37 participants, and it's also maybe also due to the non-stationarity. Non-stationarity, right? So just a quick summary of what this project is about. So we have a couple contributions. The first contribution is that we propose the use of the average reward to assess the longer-term performance of mobile health policies as an important first step to develop effective treatment policies. And we develop a flexible couple estimator for the average reward. And the third contribution is that when we in order to do the inference, and to estimate the density ratio, we develop a kind of indirect estimator for the density ratio using the couple estimation idea. There are many future directions for the future research. Obviously, this is evaluating policy is just a first step. It will be of interest to extend the message to the policy optimization problem, where the goal is to find the optimal policy instead of just evaluating a single policy. We are currently working on that, and we have an archive paper. If you're interested, you can take a look at. And also, like I mentioned earlier, in mobile health, non-stationarity is a big problem. This is mainly kind of appears as if because we don't really observe the full state of the individual. For example, like the engagement and the burden is not really observable, right? So this might act like a non-stationarity in the data. So it will be interesting to see how we can incorporate certain level of non-stationarity in this average reward framework. We might also consider other criterion for evaluating a policy. For example, we can use the total rewards over the indefinite horizon to account for the disengagement, and the disengagement is like an absorbing state. And so instead of maximizing the infinite number of rewards, we just maximizing the rewards up to prior to the disengagement. Thank you.
Thank you, Peng and Professor Murphy for the great talk. Maybe let's look at some of the questions. So the first question is sorry. It seems that you are using RKHS for approximating the Q functions, the value functions, but in the average time averaging setting, there seems to be an additional constraint on the Q function, that is the expected value of the Q function, where the action taken from the policy and the state drawn from the stationary distribution, that expectation is equal to 0 because of the definition of the relative action value function. So how do you incorporate this constraint into the RKHS?
Right. So yes. So because our goal is to average to estimate the average reward instead of estimating the original value functions. So we only target one specific version of the value functions. So in this work, we kind of constrain the space so that the value is equal to 0 at a particular state and actions, and this can be achieved by modifying the kernel. And we have that formula in the paper. Right? Does that?
Thank you. And another question is regarding on your asymptotic variance that you presented. It seems that there's a density ratio between this d pi and dt, and I was wondering whether this dt is also random, a random variable, or it's a deterministic quantity.
This is a function of, it's a deterministic, it's a function of state and actions. It's just the average density of the average density over t time points, right?
Okay,
I'm not sure if I, yeah, okay.
So you mean that like lowercase d sub t, that itself has the expectation in it. Am I right, Peng? That lowercase d sub t has an expectation inside of it. It's the distribution of the state. Yeah.
It's the marginal density for that, for the state action at that time t. Right. So there.
Thank you. And also, I was wondering, in terms of the estimation error, what kind of assumption that you impose on the quality of the sampling distribution? That is the regularity of the behavior policy. It's in reinforcement learning, there are also other kind of additional assumptions on the sampling distribution. Say the covariance of say the density is lower bounded everywhere, or the bounded contributivity coefficients, etc. And what type of regularity?
Yes, so we do have to assume the action selection probability. The behavioral policies, we have a strictly positive. We have a lower bound for that, and we also assume that. Essentially, we also assume that for every state we have a positive. The density is positive everywhere under the behavioral policies, so that the subnorm of this density ratio is bounded.
I see. So this density ratio should be bounded everywhere at each state action pair.
Right.
I see. Thank you. And also another question is it possible to extend this work to the other settings of reinforcement learning, say discounted and finite horizon?
There is existing work for the discounted formulation and the finite stage problems, and based on similar ideas.
Thank you. And another question is from Homa, and the question is, how do you evaluate and validate the effectiveness of your proposed decisions to participants in clinical trials? Is there a clinical ground truth to show that this method improves the health condition in patients?
This is a very good question, and Susan, do you want to?
Well, so in the original 42-day study, there was a primary analysis that was pre-specified. It was actually registered with clinicaltrials.gov and Open Science. No, not with Open Science, I think this time, just clinicaltrials.gov. And in that analysis, the whole procedure was pre-specified. And there it was whether or not there was an increase in step count if you got a message versus if you didn't. And the data was pretty clear that it's a 6-week study. So for the first 3 weeks, there really was strong evidence of an increase in people's activity and no decrease in their it wasn't like they didn't change their activity to just be around these 5 times. But around midway through the study, like 3 weeks in, the data analyses indicated that treatment effect dissipated. And that was, that actually is one of the reasons why there's 2 further studies where we have Peng's developed online reinforcement learning algorithms in the 2 further studies. But that data is not being considered here. Of course, the game is that once you have a good RL algorithm, you'll test it in a 2-arm trial. where one arm just gets an appropriate control and the other arm gets the algorithm. But right now, all of these trials are about optimizing the intervention, building it up prospectively.
Thank you. And so I'm running out of the questions, and thank you again for the great talk. Thank you, Professor Murphy, and thank you, Peng.
Yep.
And also thanks everyone for coming today, and we are looking forward to see you guys next week.